Good morning, February 10th. Let's carry on with problem 3. I read it very carefully yesterday, part D, and read a little of part E. And now I have the definitions of the zeta and L functions, and then it occurred to me that we might need some of these apparently disconnected things of from problem 2 and the formula we derived, and note the minus here because there's no minus here. So let's start up here. So we can either start on the left-hand side or right-hand side. Since we should set chi of h outside parentheses, I think we should start here and then collect the residues. And I suppress chi point s. And where do we sum? It must be from 1 to infinity, don't you think? And then we collect the different residues. Oh, they don't include naught nor n, and that's because chi of those values vanish. So let's just take that out. Oh, then we can just call that n times n. Where n goes from naught to infinity. Ooh, I'm getting this, I think. So this is of course equal to chi of h. That was the whole idea. And here we could put n to minus s outside parentheses. And then we get h divided by n plus n to minus s. Now, need we care about convergence? We can always assume the real part of s is larger than 1, or rather we must assume that. All right. And then summing over n, that gives exactly zeta. Oops, the sum over h zeta of h divided by n point s comma s, and that's what we have to prove. All right. Well, it really looks as if we are going to combine these two formulas here. I believe we should start with this guy, so I should have written it here instead of. All right. It's always a good thing to write the formula once again. I don't know what to do about this change of sign. Oh, we have chi bar, so that is that we get a g of chi conjugate. It's just the conjugated we get, perhaps. So let's see what we can do. Let's just use it as it says. I have to do the opposite of what you did up here. And of course this A confuses me, because this A is probably the residue. If we say we choose A between 0 and capital N, then it's A divided by, this A is A divided by capital N. So that's the A, oops. This guy should be the A we use up here. And then when N is, when we add capital N up here, then this gives the same. I'm going a little in circles here. It says we have to work on chi bar here. I need a little break to collect my thoughts. I have some abstract ideas, but I can't get them down on the whiteboard. So we'll just take a little break. I had my break, and I wrote up the right hand side here, and then we get g of chi bar times g of chi and by problem 9 of section 2 that's equal to chi of minus 1 times the norm of the ideal, which is n. And of course this only holds when chi is primitive and non-constant, as well as this formula only holds for chi being primitive. So g of chi times g of chi bar gives chi of minus 1 times n, which cancel, and then the same sum over a and n. So I'm back to my idea, writing n as b plus in. And I just being naught and the positive negative integers. So let's see what that gives. And we disregard the in up here, so it's just BAB divided by n times b plus in to minus s I don't feel that we are getting any closer. We're just doing this, we're just coming back to something approaching this formula. Yeah, I feel this is the wrong idea. I'll stop recording for now then. There is one more thing I'll try before I call it quits. And that's just working on this guy. This holds some promise, really. And maybe I should write that being all integers, of course. And then let's only work with which one should we divide by, a or n? I think it would be reasonable to have chi bar of n divided by a, and then we only take a in the multiplicative group. Where's the n? Oh, we don't have an n there. Well, it seems it was staring me right in the face and I didn't see it. And then this equals minus a, so we just change variable and call it h instead. And then summing this guy. Now, I have to be careful here. We shall have L. So, chi of h, and n sums from 1, like it does here. So it's just L h divided by n, comma s. And wasn't that the formula we should... That was exactly the formula I should prove. So this was really simple, but it's difficult to do while recording, of course. So let's just get started on E. We have an even character, and then now that means we can couple an h and then minus h, which of course is 1 minus h up here. So we pair them. That requires n being odd. So I'll just isolate L of chi point S, chi comma S, that looks like in S, equals Yeah, I'll just take 1 divided by g of chi bar and then we collect h and minus h. So they have the same chi. And in problem part C, we proved that these are entire are they entire? Yes, that this is an entire function. So the finite sum of the finite number of entire functions is entire, and then we must what must we do really? Then we must use the other formula and isolate L here, and then chi and chi bar of 1 minus s. That seems like we must use the functional relation of problems of part C. I can't do that while recording, so I'll make a new, it'll probably be later, a new page where I write it, and then I'll record it, and then we'll see what happens. I wrote the two formulas for L of chi and L of chi bar and isolated the L's, and then we must use the answer to problem C. So the left-hand side of the relation is pi to minus s halves gamma of s halves times this parenthesis and this factor and then the L functions times pi, so 1 minus s halves gamma of 1 minus s halves, and then we shall apply this guy, that this sum equals g of chi and then just copy the rest. So, gentlemen, this is my relation. Of course, gentlemen of all conceivable sexes. There's just one little thing I missed, and that's the s here. That must be 1 minus s. There we go. That was E. Right. And I haven't read the next part carefully, so I'll just make a pause. I read it not very carefully, but I think I've got it. We apply the formula up here to s equals 1/2. And then pi, when s is 1/2, this is 1/2 divided by minus a quarter. Yeah. And we just do it again. Yeah, still a quarter. And we were informed in the problem here that chi is a quadratic character, meaning it only has real values, plus minus 1. And that implies, of course, that these two are equal. So if they're distinct, we immediately get the result they require. Nice. Let's see if I can just make a little break and then take part G. So I found the page where I concluded the zeros of this sum with the zeta functions, and that was at 0, -2, -4, etc. And that means the zeta function here in this formula have zeros at 0, -2, -4, etc., which is inherited by L then. First I only used the L function, but then we missed the one at 0, at s equals 0. All right, that was F, or was that G? My God, that was G. I've had my lunch and is now ready to answer or work on part G. We have zeros of L at S equals 0, -2, etc. And that they are cancelled here by the poles of the gamma function. So let's just take the last two guys. And we shall then differentiate at the 0. So and then we must let S tend to -2k. Then we get the residue of the gamma function, of the pole of the gamma function. I don't really know how to write that. We need to find the residue of the gamma function at the negative point. So that's something I can look up, but I'll try to find it myself, applying the multiplication function, which is in the book. Well, let's multiply with sine and divide by gamma of 1 minus s. It's a little word. Shouldn't it be s here? That sounds like modern mathematics. Right. I'm not wearing my glasses, so I misread the s for an x. And we divide this guy by s plus 2k and multiply this guy. And the derivative of sine pi s at the even negative numbers, we'll just plot the sine so I can see it. Oops. So the derivative here is pi. I forgot the gamma. And this tends to gamma of 1 plus 2k and that's the factorial of 2k. All right. So it's a pi cancel. So it's 1 divided by 2k factorial. All right. So I've totally forgot where we came from. That was the part. Let me just delete this. It's taken up too much space. So now we can just let so this was the limit. Yep, so it's n to minus 2k gamma of what? Oh yeah, that was 1 divided by 2k factorial. Equals and then g of chi times of 1 minus s, that's 1 plus 2k, pi s is minus 1 plus 2k and gamma of 1 plus 2k halves Well, was that not what I was asked to do? Express in terms of, so we should isolate it. right? And finally, we should specialize to k equals naught. That's unity, that's 1. And pi to minus 1/2. Gamma of 1/2. So we need to find out about gamma half, and that's also a value one should just know, which I don't. So we go back to the reflection formula for the gamma function and setting s equal to 1. No. Oh yeah, setting s equal to 1/2, we get pi divided by sine pi half, so it's pi. So that means that this is square root pi. So they cancel. And the next thing was, did we know g of chi in this case? No, we do not necessarily. All right, that finishes problem, what was it, 3, only 3, but they are long.